Okay, question 6 from the 2016 AP Chemistry FRQs was one that kind of threw people across the nation here. The average score on this was less than 1 point. And I think there are a lot of things that kind of explain. First off, what is EDTA? EDTA is ethylene diamine tetraacetate, or tetraacetic acid. But in this case, you can see what happens is that, that lost the H there, lost the H there, lost the H. So it's not acetic acid, it's acetate. And having those highly electronegative oxygens and the highly electronegative nitrogens, okay, those can surround a metal ion, and it's called chelating. And sometimes it's used to remove ions, EDTA. Anyway, you don't have to understand that at all in order to be able to do the problem, but for a lot of people, I think that pretty much threw them off. So an ion, barium plus EDTA 4- turns into barium EDTA 2-, and this is a coordination compound, and it does have a constant, okay, when it forms like this, called a formation constant, and that constant is 7.7 times 10 to the 7, which we should notice that is a big number, okay, which means this equilibrium is very, very, very product favored. Pretty much this reaction is going to be almost one way. It's just going to go to reaction. So here we go. The polyatomic ion C10H12N2O8 4- is commonly abbreviated as EDTA 4-. The ion can form complexes with metal ions in aqueous solution. A complex of EDTA with barium ion forms according to the equation above. Now, here's some important stuff. A 50 milliliter volume of a solution that has a concentration in EDTA of 0.3 is mixed with 50 milliliters of 0.2 molar barium nitrate to produce 100 milliliters of solution. So part A, considering the value of K for the reaction, determine the concentration of BA EDTA 2- in the 100 milliliters of solution and justify your answer. So, considering the value of K, okay, that K is big. So what's going to happen, this is not an equilibrium problem because that is so big, and basically you're not going to have all three things. You're just going to go forward until something runs out. So this is really a limiting reactant problem. Now for limiting reactant problems, we find out, well, how much of each of the reactants do we have, and then figure out who's going to run out first. So personally, I would do this as a icebox problem because it helps me kind of organize my information. Barium EDTA, and that'll be 2-. So 2+ and a 4- gives us a 2-. And so what do I know here? I know that for my chemicals to start with, okay, I don't have any of this barium EDTA. Okay, we have some barium though, and it says we have 50 milliliters, 0.05 liters times 0.2 molar. So when I multiply that, I get 0.010 moles of barium. And for the EDTA, it's the same kind of thing as 0.05 liters times 0.3 molar. So that's going to be 0.015 moles. So we can see who's going to run out first is the barium. So how much are we going to use up? We're going to use up 0.010 moles. We're going to use up 0.010 moles. And we're going to make 0.010 moles. So this is going to be 0, this is going to be 0.005 moles, and this is going to be 0.010 moles of this barium stuff. Okay, so the real question is, what is the molarity of this? So it's the 0.010 moles in 100 milliliters, 0.01 liters. So when we're all done, that's going to be 0.10 molar BA EDTA 2-. And that's the first part of the answer. So 1 point is for recognizing that this equilibrium is going to pretty much, go to completion. So that's 1 point's worth. And then 1 point is for actually getting the concentration based on that. Okay, the part B then we're going to say the solution is diluted in distilled water to a total volume of 1 liter. So we're going from 100 milliliters to 1 liter. So we're diluting everything by 1/10. After equilibrium has been established, is the number of moles of barium in the solution greater than, less than, or equal to the number of barium present in the original solution before it was diluted? In other words, we're looking at this guy here, and we're saying, well, if we dilute it, is this guy going to shift to the left and make this increase? Is it going to shift to the right and decrease? Or is it going to stay the same? Okay. Well, if we want to talk about different, solutions and what happens to them, a good way to do that is with Q. And so Q is going to be the concentration of this barium EDTA stuff. 4 minus 2 plus, okay, 2 minus. Okay, divided by the concentration of barium and the concentration of EDTA. Okay, and that equals some value of K. But what we're going to do is say, well, they're going to dilute it down to 1/10. So it's really 1/10 of this over 1/10 of this and 1/10 of this. Now, a lot of people said, okay, well, since you're diluting everything, it's not going to change. What it does, because you have two things here in the denominator, you only have one thing at the top, the numerator. So what's going to happen is, the 3 red parts here, that's going to turn into K, but 1/10 and 1/10, that'll cancel out, but I still have a 1/10 on the bottom. So what I'm going to end up with is Q is going to be equal to 10, whatever the constant was. Okay, so 10 times constant. So in other words, Q is greater than K, and if Q is greater than K, then you're going to have to form reactants. This guy's going to shift to the left. Okay, so there's going to be more barium. Okay, so the barium concentration is going to increase for this reaction to reach equilibrium again. Okay, and that's the answer, and that's 2 points. Okay, one for saying that the barium concentration increases, and then another one for having some sort of a good verification, justification why it would do that. And if you want to do Q versus K, that's a useful thing. Le Chatelier is a little tough. You say that, you are so how they say this, that the number of moles of barium increases because the percent dissociation of barium EDTA 2 minus increases as the solution is diluted. That's the scoring guidelines, and I don't get that at all. Okay, but now this is a question. I didn't get this right. I tried to do a KA thing on this, and I just made a big mess of it. So nationwide, most people made a mess of this as well. So that's question 6, something to learn. So again, there is this kind of funny thing going on, but you didn't have to understand that to do the problem. What you did have to notice was that was a big value of K, so therefore this is very product favored, and it's a limiting reactant problem, not an equilibrium problem. And that's number 6.